Okay, so let's start. Yeah, welcome back after 1 week. So hope whoever was traveling had a good time. Before we left, in the last class at least, we were looking into control sources, how to make control sources using the incremental model of a transistor. We covered 3 control sources. We'll cover the other one also, but I mean, in a different context later on. So what I want to do now is to draw your attention to the fact that when we did particularly a voltage control voltage source, we made one simplistic assumptions that a voltage control voltage source is nothing but V naught should be equal to K times Vi, where K can be anything. But the realization that we did was for a particular case of K equal to 1. Okay, so the aim of this course is to essentially design VCVS, but not with a gain of K equal to 1. It can be anything. Okay, so that's what we would like to see here. The framework of what we need to do has already been laid. We'll formalize it and see how to proceed along those lines. The other thing that I would like to draw your attention to is the fact that you must have noticed that we have been ignoring capacitors till now, right? So there has been no capacitors in any of the analysis that we have done. However, in real life, all transistors you see will always have some capacitance, because by the definition of a MOSFET, MOS stands for metal oxide semiconductor, and the junction itself is a capacitance. So you would like it or not, capacitance exists, right? So to make our life easy, we have been ignoring the capacitance, but we'll have to take into account what happens if we put capacitance in the first place. Now, very briefly, you can imagine that if you put a capacitance in, let's say you have an R by R network, like a voltage divider R by R. Okay, so let's say you have a voltage divider and you put a step at this node, and you're observing that this node, if this is both R, what do you expect this intermediate node to be? It should be a step again, but the half of whatever it was initially. Okay, so however, if we just put a capacitor here inadvertently, because capacitors cannot be neglected, what will eventually happen is that this step will not be as sharp. There will be some profile to it. So essentially it will settle to wherever it needs to, but it will settle after some time. So you can think of it in such a way that the capacitor to some extent delays the steady state, right? So whatever the steady state we want to reach, the effect of capacitance is essentially to delay it. Now, how it delays depends on how the capacitor is connected, so on and so forth. And also it depends whether the capacitor is connected in parallel, series, and those considerations. As it turns out, if you connect capacitors in certain circuits in a certain way, it can also advance your input, advance the output. But those are the things that we will see. We'll see later. The key point that I would want to emphasize here is that if you want to check the time response of a circuit, right, you have to understand that nothing in this world will respond immediately. Okay, only our theoretical models are good enough to model something which is supposed to respond instantaneously, but in reality nothing responds instantaneously, which means we need to figure out a way of modeling these time lags. Okay, so when you do this, even if I take you back to the ideal op-amp circuits, right? So if I take you back to these type of circuits where you assume the op-amp is ideal and so on and so forth, you apply an input here, the output appears directly here immediately, right? So this is good as long as this type of modeling is good enough as long as you are not particularly interested as to how the output is settling, but you are only interested in steady state. But as we will soon see, that is not good enough, because ultimately you will not design circuit and wait for one day for the output to settle, right? You would want your phones and computers to be as fast as possible. which means you need to know what is the effect of these things, which essentially means that we need to figure out, we need to understand what is the what is the effect of these capacitors, or what is the effect, if there is at all any effect of on these transistors, or whenever we'll be making the op amps, when we put these capacitors in, when we introduce this capacitance, right? So to notice that the characteristics of our transistors or characteristics of our amplifiers under the condition that there will be some time response associated with its output. Okay, so with that introduction, let's delve into negative feedback in a more formal way, but in a slightly more mathematical, with a slightly more mathematical framework in the background. Okay, so essentially what we were, as I started this lecture, I said that we want to make an amplifier or a voltage control voltage source where V0 is K times Vi, where K is greater than 1. Okay, so we want to make this. So, and we want to make this using negative feedback, because we saw right at the beginning of the course that if we just use our transistors to get some Gm times R kind of gain, where Gm times R is greater than 1, the problem becomes that it is dependent on temperature, ambient variation, and so on. So which essentially means that this K, we want this K needs to be accurate. Okay, so which directly means that the open loop way of making an amplifier will not suffice, because an open loop way of making the amplifier will essentially lead to the fact that it will depend on the characteristics of the small signal models of the amplifier, which are namely GDS, GM, and so on. So we have to make sure this K is independent of those parameters. And we saw how we do that when we didn't take these capacitors and all these things into account. We were making control sources, and we figured out how to do that by putting things in negative feedback. Okay, so this is essentially an extension of that. So before going into before delving into both this, how we make K to be greater than 1 and how we incorporate the effect of time into the design. So what we will do, we'll again what I'll try to do is I'll try to lead you through an analogous example, and the one that really helps drive home the point is that of riding a bike, right, or something like that. So so imagine yourself that you are riding a bike, whatever be it, I mean, your choice. So let's assume that you are on a highway and there's a limit of 40 kilometers per hour or whatever. So you would like to hit that 40 kilometers per hour. You don't want to undershoot, you don't want to overshoot, because obviously you don't want to undershoot because you want to have a good experience. You don't want to overshoot because obviously, I mean, traffic lights, right? So let's say you want to achieve a goal of 40 kilometers per hour. So this is my desired speed, right? So anything with negative feedback, you'll see there is an actual output, there's a desired output. You try to minimize the difference between the desired and the actual. So this is the desired speed, and you have an actual speed, right? So let's call it S out. Okay, so you have an actual speed. Now how do you figure out what is your actual speed? I mean, let's say you cannot see the environment and trees flowing past and all those things. How do you figure out? Speedometer, right? So you look at the speedometer, that gives you a reading. So you have a speedometer. That gives you a reading. And you look into the reading, and let's say the speedometer reading gives you like 10 kilometers per hour. So what will you do? You have, I mean, you see, I'm going slower, I can speed up, right? So essentially the math that you are doing in your head is you are comparing this expected desired speed of 40 kmph with 10 kmph, and you are calculating a difference in your head. I mean, everything is being done automatically. You are essentially taking a decision based on the difference of your desired and actual. So in electronic, I mean, in a electronic format, this is essentially modeled by a difference, by a difference block, right? So essentially you get a difference of 30 kmph. And then what do? You essentially you have an accelerator pedal. You nowadays you don't have pedal, you have this. So you essentially step on the accelerator, and essentially that changes the speed. You observe the speed, and this goes on and on, right? So when will this entire negative feedback loop settle? Ultimately, when you see that speedometer output reaches 40 kmph. Okay, so when the speedometer output reaches 40 kmph, you'll say, okay, fine, whatever the, my error voltage here, error speed here is 0. But whatever pressure I was giving on the accelerator is good enough, I'll keep it there. Okay, so essentially the output will essentially be your the output will be the speed that you would like to go at. Okay, so this is, I hope this is simplistic enough, simplistic enough model for everybody to appreciate, because what we will do, we'll take this model and then see how we can draw inspiration for our electronic feedback systems. Okay, so so the key thing here is that even before I go into the details of how to model this, couple of comments, which we essentially have a summer or a difference or a block that takes a difference, and an accelerator and a speedometer. So let's forget about the taking the difference thing. We can let's only concentrate on the accelerator and your speedometer. So among these two, which one do you think is more important if you are looking for accuracy? Like, I don't want to absolutely overshoot or undershoot 40 kmph. Speedometer, right? And why not accelerator? I mean, let's say you have a fast bike and you have a very slow bike, which means accelerator is different, right? Your rate at which you can speed up is different. So why not accelerator?
So accelerator is deciding how fast we can go.
Right. Yeah. So accelerator essentially decides how fast you will settle, but it has no bearing on whether you will eventually, at what velocity you will settle to, right? So if you have a poor accelerator, you will probably take 1 day to settle, but if you have a very fast accelerator, you will settle in a couple of seconds. That's a different issue. But whether you will be reaching steady state and settle to whatever velocity you want, that doesn't depend on the accelerator. It depends on the speedometer, because if the speedometer is giving you a wrong reading, you will take a different action, and which essentially will lead to a different output settle speed, right? So which essentially means that the speedometer needs to be very accurate. Okay, and your accelerator can be okay. I mean, it can be inaccurate also. You don't really care. So in a circuit design parlance, which essentially means that our transistors or whatever we are trying to put, it should be put inside this block of accelerator, and whatever very accurate stuffs that you want to put in the speedometer. Okay, and this is again in the standard feedback topologies that you have studied in control system courses. You must have seen that this V0 over Vi, as long as GH is much greater than 1, V0 over Vi is essentially 1 over H, right? It's not dependent on G. So so the analogy is essentially identical. Okay. So now that we have established that this accelerator is supposed to be the stuff which contains our transistors, we need to figure out what is the characteristics. I mean, what type, since this block itself has a through the argument itself that I laid out, you could appreciate the fact that there's a time dependence to it, right? So you are taking an action based on an output, and the action is also being taken after the output, after some change in output, right? So there's a time dependence to it, and there's a settling action to it, which essentially means that we need to figure out what is the settling characteristics of accelerator, or the time domain characteristics of the accelerator. Now the issue with this, any feedback system, the analysis of any feedback system becomes slightly tricky because it's in a loop, right? So when things are in a loop, you don't really understand whether what is the cause and what is the effect, because everything affects everything in the loop. Now, if you have to do that, somehow you'll have to break the loop somewhere and then see what is, I mean, then you break the loop, and then if there is nothing that is returning back, right? If the loop is broken, then I can apply certain input and then argue what the output should be. So that's what we will do here. And let's assume that your speedometer is broken, right? So speedometer is broken. By that I mean that your speedometer is stuck at, it's a 10 kmph. Whatever you do with your accelerator, speedometer always gives you 10 kmph. Okay, so you have this block. But the speedometer is always stuck, which means this is not there, and you're always getting 10 kmph. And your desired speed is 40 kmph. So your error speed is 30 kmph. So what do you expect the output to be? Okay, hold on. So your error speed, let me call it VE, velocity. I mean, so error velocity is 30 kmph. What do you expect the actual output velocity to be? What do you expect the output profile of V0 to be? It should increase, right? Anybody has any doubts about that? So essentially, let's start from time t equal to 0. You are already, sorry, yeah. So you are already seeing the speedometer output to be 10 kmph. In your mind, you calculated that the difference is 30 kmph, which means you're thinking that I need to go fast, right? Because I am not really going at the speed that I desire, which means you will step on the accelerator, right? But and then you will see that still I am at 30 kmph. Still I am at 10 kmph. I'll keep on stepping on the accelerator. So if I keep on stepping on the accelerator, what will happen to the output? It will keep on increasing, right? So it will keep on increasing. Now, depending upon the characteristics of your accelerator, it might go like this, it might go like this. It doesn't matter, but essentially you will be monotonically increasing. That's the desired output and the desired characteristics of your accelerator. Now, for the purpose of simplicity, and you will see why later on in the course also, we'll check the simplest possible monotonic thing that we know, that is a straight line. Right? So it will increase at a certain rate, and the slope is dependent on the input. Okay. So now let's take another example. Let's assume your speedometer is stuck at, let's say, 30 kmph. Right. So let's say speedometer output is stuck at 30 kmph, which means the error voltage is error speed is 10 kmph. So what do you expect the V0 to be now with respect to the magenta line? You would expect still to increase, but since you know that you are pretty close to my desired output speed, you wouldn't want to accelerate too fast. You would want to accelerate slowly, right? So, which essentially means that your output is, your input is a step, right? Input is a constant slope, is a constant which is not changing with time, but your output is a ramp, and this ramp is also, the slope of the ramp is dependent on the input, right? So what type of characteristics is this? What in terms of time, I mean, what is this block supposed to do? It's supposed to integrate, right? Input is constant, output is slowly ramping, right? And this integration is also the proportionality constant of the integration is. Can you comment on the proportionality constant of the integration? It should be constant, or it should depend on something else. Will the proportionality constant depend on V, or the output depend on V? The output should depend on V. So the proportionality constant will be a constant. Okay, so this essentially, so this block, your accelerator, at least from the model that we have seen right now, will be an integrator, and you will have a proportionality constant which is constant, because if it's not constant, then obviously, I mean, you don't get this constant slope, right? So it will be something else. So now, yeah. So by the way, any questions till now? Everything has been very heuristic till now, but any questions? No? Okay, fine. So now that we have established that this has to be an integrator. Now, from the perspective of, let's shift to the voltage domain now. I mean, this is an integrator, but I don't mean voltage domain, but let's now shift our attention to the fact that how it is going to settle. Okay, so now let's assume that, let's go back to this model again. Now let's assume this loop is closed, because now we have figured out what this characteristic of the accelerator is supposed to be. So now let's assume that at time t equal to 0, I started this entire process. My desired goal is 40 kmph. At time t equal to 0, what will be VE? VE will be 40 because my output is 0. Let's say this is V0. So my output is 0, my VE is 40. So I am taking an action, and what is the action? I am stepping on the accelerator. And what is the rate at which the V0 will change because of this? So input is 40. Input to the accelerator is 40. 40 into omega u, right? So it will change at 40 into omega u kmph, right? Or rather kmph per hour, because now it's at the rate, right? So the slope will be, increase, or rather you will have a slope, and then what is the effect of this? The effect of this is your feedback speed has increased, which means this 40 is going down, right? So this 40 is going down. Now, because this 40 has gone, I mean, this error speed has gone down, what will happen to the output? Rate at which the output is changing? It will decrease, right? So your rate at which your output is changing will decrease, and this will keep on going on, right? So I'm showing it in a stepwise manner, but this is happening in a continuous time manner, right? It will not be a stepwise manner. And ultimately, when will this process settle? Output reaches 40, right? So when output effectively reaches 40, the error voltage will go to 0 and it will eventually settle. Okay. So now the question to you is that why does the output need to reach 40? I mean, why can't it reach to, let's say, 39.9 or 40.1? What characteristics of this feedback loop ensures that the output reaches 40? The difference will always be there, and exactly, and if the difference is there, what happens? If you have a finite DC difference at the input of an integrator, the integrator will keep on driving, right? So essentially, an integrator, in an ideal integrator in a negative feedback loop, cannot sustain a DC offset. Okay, so this makes sense, because if you have an ideal integrator, what is the DC gain of an ideal integrator? Infinite, right? DC gain of an ideal integrator is infinite. It's like an ideal op-amp. If you have an ideal integrator, you have infinite gain. Naturally, when you put an infinite gain block in a negative feedback loop, its input error voltage or whatever the error you are observing has to go to 0. Otherwise, it will keep on driving, right? Make sense? I see few blank faces, so that's why I'm asking. This is very crucial, right? So this is, I mean, you've already seen this in earlier lectures, that how infinite gain helps you make something similar to an ideal op-amp. This is the same thing, but approached from a different perspective. And yeah. Okay. So let's see. So his question is, when I say for DC input you have infinite gain, what do I mean? So if I see an integrator, right? So what is the Laplace transform of an integrator? Omega u by s in this case, right? So at DC s is 0. So you have infinite gain, right? So this is in the Laplace domain or even in the frequency domain. But in the time domain, how do you reconcile infinite gain? It's essentially the fact that if you have, when you say something is happening at DC, which means you are waiting for infinite time, right? Zero frequency means infinite time waiting. So if you have an integrator, give a finite step and wait for infinite time, the output will go to infinity, right? It will keep on ramping, ideal stuff, right? Which means you eventually you have a finite input, infinite output, you have infinite DC gain. Okay. Okay, makes sense? Okay, this is one of the other reasons why only having very high DC gain might not suffice in all designs, because ultimately in order to reach that effect of DC gain, you might have to wait for long enough time. Okay, so among whatever you are seeing in this loop, which characteristics or what in this loop determines, which variable in this loop determines how fast you are going to reach your steady state? Omega u, right? Because if omega u is high, which means the slope of the ramp is high, wherever you want to reach, you will reach quickly. Now, I mean, one might always argue that I will never reach in a steady state because it's asymptotic settling. But we are not, I mean, bothered about reaching the exact. Maybe you can settle that I want to reach 99% or 99.99%. Whatever limit you set, you will reach there faster if omega u is higher and higher. Okay, so another design constraints that designers will face, you'll also see in your in the upcoming lectures, that we not only want to make a negative feedback loop where you get good enough gain and so on, you would want to reach that output at as high speed as possible, which means essentially you have to make you desire omega u to be as high as possible. Okay, does that make sense? Okay. So now let's gravitate towards the electrical analogy of this. So we would like to make V naught equal to K times Vi, where K is greater than 1. So now when let me take you back to the process of synthesizing a negative feedback loop. So one of the first things that you do, I mean, some things are interchangeable, but one of the first things that you do while creating a negative feedback loop is to define what is a desired and what is an actual, right? It is only then you can take a difference. So in this case, I know that my desired output is K times Vi. Okay, so my desired output is K times Vi. So my actual output equal to V naught. So the first thing that we have to do is to manufacture a difference, right? Because if we only take if we want and only manufacture a difference, I can take a decision based on the difference as to how to drive the output so as to make the difference equal to 0, right? So I manufacture a difference, VE equal to, let's say, V naught minus KVI. Okay, and the idea is to drive this to 0. Okay, so now you have, okay, so now what is the issue? I mean, can I use this argument to set up my negative feedback loop in the first place in a practical scenario? Note that K is greater than 1. So I have a V naught, right? I have a V naught, and I want this V naught to go to KVI, right? And for that, I am saying I have to compare V naught with K times Vi. Is that possible? Because if it were possible, I wouldn't have, if I already had K times Vi, I wouldn't go into all this pain, right? I don't have K times Vi. And again, note that K has to be independent of the GM and all those things, right? So I cannot say that I'll amplify VI and then compare, because that is something that we are trying to avoid. So you cannot do this. However, note that you can do one thing. You have V0, let's say, and you put it through a resistor divider. And let's say this is, I'm giving you an example of 1 by 1 in R by R case. So this V0 is equal to, sorry, this output, let's say Vx, this is equal to V0 over 2. And this is independent of R. Okay. And a good thing about IC design is the fact that you can place these resistors or whatever components that you can get very close to each other, and they match each other very well, which essentially means that if the temperature characteristics of R, the process characteristics of R will be identical, even if they are two different resistors placed close by. Okay. Essentially, if you consider these resistors to be functions of ambient condition variation, both of these resistors will go in the same direction, in the same way. It will vary in the same way, which essentially means that it doesn't really matter if R is, 1 ohm, or R is 10 ohm, or R is 100 ohm. It doesn't really matter as long as both the brothers are doing the same thing. Okay. So we can do this. We can take, which essentially means that we can do something. We can attenuate things very accurately. Okay, but we cannot amplify things very accurately as is. This is an open loop way of attenuating, right? There is no negative feedback, nothing. Right? So an open loop way of attenuation is far more accurate than an open loop way of amplification. Okay, so given this background, what do you think? How should I go and set up my negative feedback loop? Because K greater than 1 is not possible. So what should I do? Yeah, right. So essentially, comparing this is equivalent to saying that I will compare V0 by K minus Vi and drive it to 0. Right. So if I redefine my VE, to be equal to this, and I can drive this VE to 0, I will achieve the same objective. There's no difference between these two cases from as far as obtaining the final goal is concerned. Make sense? Okay, so this we can do because K is greater than 1, V0 over K is essentially attenuating V0. So I have V0. What I'll do, I'll put it through a resistor divider. Let's say this is K minus 1R. This is R. So clearly this is V0 over K. Okay, and this is pretty accurate. So now I said that, I'll compare it with VE, compare it with the VI. So this is VI. So now whether this error voltage is V0 over K minus Vi or Vi minus V0 over K, how will you determine that? Because ultimately, if this goes to 0, it doesn't matter whether it approaches 0 from positive side or negative side, right? So how will you, essentially what I'm trying to say is that how would you ensure that the signs of this, this sum are like this or like this?
Feedback has to be negative. Otherwise, this will increase.
Correct. Feedback has to be negative. And how will you ensure feedback has to be negative? We haven't yet closed the loop. Yeah. So essentially, first we have to close the loop. And we said that this stuff inside the loop, this forward path essentially has to be an integrator. So we say that this is omega u t. And then we take a call, right? Initially, we don't know whether these signs have to be plus on the positives on one side, on plus on the, on the Vi side or plus on the Vo side. So now, as he pointed out, that we can take a call based on seeing, let's assume hypothetically, anywhere in the loop, a voltage increases. You can assume V0 increases. Let's assume V0 has increased. If V0 increases, clearly this has increased. Now you start off with any sign convention. Maybe you start off with the green sign convention. So if this has increased, then this will increase. If this increases, the integrator is driving the output to higher value, right, in the positive direction, which means that I am in a positive feedback loop, right? It's not trying to negate any change, it's trying to amplify the change, right? It's reinforcing the change. The integrator is operating in completely the opposite way that I want it to. So there are two ways to fix this. I can say that I will change the sign of this integrator from omega u to minus omega u, or I will change the signs of the summer, right? So let's do the second one. So this becomes my negative feedback loop with the desired directions. Okay. Any questions? Okay, fine. So now if this is the scenario, we are now in a position to figure out what are the dynamics of V naught with respect to Vi in terms of how it settles with respect to time. So let's assume that Vi is a step. Okay, let's assume that Vi is a unit step. So we can set up the differential equation, and I mean, it's always easier to set up a differential equation when everything is in differential form, but you see that you have integrator in the loop also. So what I will do is I will refer all the voltages to the input of the integrator so that we get rid of the integration, right? So essentially this VE is 1 over omega u dV naught dt, right? So VE is 1 over omega u dt. This is Vi minus V naught. Okay. Okay. So this essentially means that so this is my governing differential equation, and if Vi is a unit step, what will be V naught? This is a first order differential equation. You must have seen it thousands of times before this, right? Pardon? So Vi is a, let's assume Vi is a step. So what will be V naught? I think I made a mistake here. This should be omega u here, right? Yeah. So if you are not sure, solve it and tell me. Yes, what will it be? Minus T by or omega u by kt, right? Okay. Okay, so you can solve it either in the classic first order differential equation solution mode, or you can also go into Laplace domain and then invert and whatever. But I mean, I presume you have, all of you have seen these type of settling equations multiple times. So essentially, what how will this settle? This will go to something like this, unsettle, where k is greater than 1, so ultimately it will go. It will overshoot the input. It has to. Okay. Any questions? So what is in any type of this first order settling, what is the most important thing that you are looking at? Time constant. And what is the time constant in this case? Yeah, a by omega u, right? So, or 1 over omega u by k. You will see this omega u over k will keep on repeating across, I mean, in a negative feedback loop in different formats. So this omega, keep an eye on this omega u by k where it goes. And obviously this this initial term of k is the DC gain that we are looking at initially, right? We wanted this to be we wanted output V naught to be k times the input. If the input is unit step, output has to be k. And clearly from this equation, you see that it doesn't really matter if omega u varies by plus minus whatever. Ultimately, yes, if you wait long enough, you will always reach V naught to be equal to K times Vi for a DC input. Okay. But obviously having K to be erroneous is problematic. Okay. Okay. So this is as far as the dynamics of a first order negative feedback loop is concerned. I say first order because you only had one integrator in the loop, right? So obviously you had a first order differential equation, and this is a settling of a first order negative feedback loop. Okay. And by the way, can you comment on the rate at which this output changes at time t equal to 0? What is the slope? What is the slope? Yeah. I'm hearing many of the things. Omega u times VE, right? Is it omega u times VE? Is it omega u times VE or K times omega u times VE? Or omega u by K times VE? It's omega u times VE. Why? I mean, it should make sense because when you are starting off, your input is, sorry, it should not be VE, right? It should be VI. When you are starting off, your whatever is fed back stuff is 0. Right? So initial error voltage is total, the input itself appears as the error voltage, which means your integrator is driving at the rate of omega u times the input, right? So this again tells you that if you want faster and faster settling, you would want faster. I mean, you would want omega u to be as high as possible. Okay. Okay. So this is as far as the DC picture is concerned, but we not only want to amplify our DC, we would also like to see what happens if we put in a time varying signal, right? For example, a sinusoid. So, we already have a well-established method of figuring out how a system responds to sinusoid, and that is we first go into the Laplace domain, then replace S by j omega, and then we get that, and then we get the transfer function, and essentially that omega is nothing but the omega of the input sinusoid. So we will go in that route. So what will be the V naught over S by Vi over S for this differential equation? Something by something, right? What is that? Okay, so if I rewrite it in the form of poles, so I'll multiply by K by omega u, so this becomes K by okay. So this also should make sense because if we put S equal to 0, that is a DC, I should get a gain of K, but it says something about if I keep on increasing frequency, something else happens. Okay, so what happens that we will see. I mean, obviously you see that it drops, but why it drops and how it drops, we'll try to get an intuition of that. So if I plot V naught over j omega over Vi, V naught by Vi, where S has been replaced by j omega, and I take the magnitude, what should I see with respect to omega? How should this plot look like?
DC gain will be K.
That DC gain will be K.
AC equals to omega.
And let's assume we are plotting it in log scale, right? So if this is log scale, then this becomes 20 log K. And then all of you know Bode plots? Okay, so use Bode approximation, straight line approximations till you hit poles. So where is the first pole? Omega u over K. So till you hit omega u over K, it's a straight line. And after you hit omega u over K, it drops the rate of minus 20 dB per decade. Okay. Okay, so before we go and analyze this, you have to recognize the fact that this omega u over K also appears here. Okay, so what is happening? I mean, why is this omega u over K sneaking around every time we take a different look at this equation? So we'll look into it. We'll try to get an intuition of that first. And what is the intuition? So let me go back to a picture that all of you are familiar with. Okay, so in this picture, we see that V naught over Vi is G by 1 plus GH. Okay, now what is this term GH? What do we call it? This GH, we'll call it loop gain, right? Yeah, open loop gain, right? So it's essentially loop gain. And how do you figure out what is a loop gain looking into the loop? I mean, how do you know or calculate or estimate? Without feedback. You break the feedback. Let's say you set this to 0 and you break the feedback somewhere. You can break it at any point of the loop, doesn't matter, at least in this model. And you apply, let's say in this case, a test voltage, let's say V test, and see whatever returns back, right? So if this is V test, what returns back here is GH times V test. And what returns here is minus GH times V test. So essentially your loop gain or GH, or we normally call it L or L of S in this case, is minus of V return by V test. Okay, so if we apply the same method to our negative feedback system with the integrator in the loop, so what will we get? So you have omega u over S. In the S domain, integrator gets into this format. So what is the first thing that I will do to figure out loop gain? I'll desensitize the input first, because loop gain doesn't depend on where you are applied the input. It's a property of the loop, not where you have applied the input. So I'll apply a V test and I will check the V return. So what is V return in this case? Minus omega u by Ks, right? Because here you get omega u time by S times V test. It gets attenuated by a factor of K here. So omega u by K times S, and then you have negative sign because it goes through a negative feedback. I mean, summer with opposite sign, and you get V return to be minus omega u by Ks. Okay, so essentially your times V test, right? Yeah, thank you. So essentially your loop gain, your L of S in in this loop is essentially minus, or not minus, because it's minus V return over V test, right? L of S is minus V return over V test. is omega u by ks. Okay, so that you see that this pesky terms of omega u by k keeps on coming here also, and because it is a property of the loop, you expect it to appear everywhere. Okay, so we'll use this. We'll take this loop gain and it will fit in with the closed loop response and see whether we can draw some analogy. So what do I mean by that? So note that my loop gain mod of L of j omega, if I plot this, what will it look like in dB scale, in log scale? A straight line, and at DC obviously it goes to infinity, so we cannot draw infinity, so I will not draw DC. And where does it intersect this? I mean, this is a 0 dB line, right? So this is 0 dB. That is gain of 1, right? So where does it intersect this 0 dB line? At what frequency? Omega u over k. So this is omega u over k. And now what I'll do, I will plot this closed loop V naught over Vi on top of this plot. Okay. So note that. So let me just mark it. This is loop gain. And what is the closed loop gain? The closed loop gain will be, this will be k or 20 log k, and it will be constant till omega u over k, and after that it will go down at the rate of 20 dB per decade, right? So this slope is minus 20 dB per decade. This slope is also minus 20 dB per decade. Okay, so what I'm trying to get at here is that what can we draw an analogy between by looking into the closed open loop transfer function or loop gain, can we get a feel of what the closed loop transfer function or the closed loop plot will look like? And why do we want to do that? Is because it's always, for the purpose of analysis, it's always easier to analyze something in open loop than something in closed loop, right? This is firstly a first order system. Later on, you will see that you have higher order systems. In that case, analyzing something that is in closed loop becomes slightly trickier. However, if you know where to apply the input and where you are taking the output and nothing comes back and changes the input and so on, if it's in an open loop fashion, then it becomes far more easier to deal with those transfer functions and draw an analogy from there. So it is because of our inability to figure out intuitively how a closed loop transfer function or closed loop dynamics will look like, we revert back to something that we know. I mean, you will see that it's true for all sorts of engineering problems, that you revert back to things that you know to figure out things that you don't know. So in this case, we don't know. We don't have too much of an intuition about how the closed loop transfer function or the closed loop dynamics will look like. So we'll revert back to something that we know, that is an open loop, because open loop is easy, right? We know an integrator, if you apply a step, output ramps, but it's not very obvious how it will behave if I put it in a closed loop. Okay, so that is the main reason we'll resort to this. We are out of time today, so in the next class we will take it from here. So what I request all of you to kindly proceed to L7.